Today we're going to talk about braids. So you know how to braid, right? You take 3 strands, and well, I'm going to do it silently because it's in my mouth. So what you do is you take your 3 strands and you start braiding them. Well, So that's a decent braid. You could braid it more, right? But that's a fine way of braiding it. Now, the question is, why are we talking about braids? This is knot theory, right? But notice what happens when you have a braid. You can take that braid, one end of it, take it to the other end, and you can start closing it up. So this was the last strand here, this was the last strand here. And when you close up your braid, notice what you get. Some kind of knot. I don't know which knot this is. We'll have to think about that some today. But the basic idea is you take a braid, you close it up, and that's one way to build a knot. So let's try to make this more precise. So let's begin with a braid. So the way I'm going to draw a braid is I'm going to have some strands, whatever number you want. Let's do 3 strands. Keep it kind of simple. And I braid the strands however I want. So this one can go over this one. And then maybe the second one will go under the third one. That's kind of exciting. And then maybe this one can come and go over this one as well. And he can come and go under this one. However you want to braid it. And keep going and keep braiding it however you like. And that's your braid. Sometimes we draw a line at the top and the bottom to denote our braid. We move from the top to the bottom, 3 strands. And notice the first one didn't end up in the first position, ended up over here. You could color it. So here's our first strand. And our second strand ended up moving from the second position to the third position. That's fine. And there's our braid. But then from a braid, we can close it up. So what we do is we close it, and we get a knot. So we can take this strand, and we close it up to the first one. And we take the second strand, and we close it up to the second one. And you take your third strand and you close it up to your third strand. So braids close to give you knots. Okay, and you can tell this is a knot because if you trace your finger around it, you go from the red to the white to the yellow, and that gives you one completed component. Now, could you imagine a situation where you wouldn't close up to be a knot?
Yeah.
Yeah, what would it have to do?
If red met with red,
Yeah?
and the 2 did whatever, well then you would have like one link and then you have...
Great. So if one component, maybe goes and there's some braiding with the other ones, but then he kind of comes back. And these maybe can continue to go down. They braid some. But notice what happens. If the component that begins in the first position, so here red, he begins in the first position, he ends up in the first position, then when you close it, red would be like its own isolated thing, right? And here, if this is yellow, well, it started off in the first position, but I moved, the second position moved to the third, so when he closes up, the second is now connected to the third. So they all form one link. And so here you get a link. You have a yellow component and a red component. So a braid closes to either a knot or a link. You can have multiple components. Okay, cool. Here was the braid we started out with. But now we might wonder, can you play the game backwards? If you begin with a knot, can you turn it into a braid? That is, can I turn it into some braid that closes up into that knot? So how would you do that? Here I have some knot. I want to turn it into some braid. Can anyone think of the braid that's associated with that knot? Imagine taking this knot and cutting it right here. Notice you have these two strands coming out of it, right? Here, I'll give it some orientations. You go around, you go around, you go around. You can cut this knot right here. I'll put a center point, and that's going to become the top of our braid. And then what happens as you move around? We're going to sweep around like we're a radar or something, you know, bloop, bloop. So we're going to sweep around it. So we have these two strands. The first one goes under the second one. Tracking with that? And then what happens next? Yeah, if this is like a first strand and this is a second strand, so the first strand's the outside. Now this is the first strand out here, and it's going to go under the second one again. This new first strand is going to go under the second one again. That takes us right here, and then one last time the outside one, this first one, will go under the second one again. And it would give us, and then it would arrive back here. We arrive back there. That's a braid. And if you think about that braid, you can convince yourself that when you close this braid up, it will precisely recover the original, because closing it up is just taking this bottom, stretching it around, and gluing it to the top, which is exactly what we did right here. So now we have a way where it seems like we can go backwards as well. But can we always go backwards? See, here was kind of lucky, right? It's like, it wasn't too hard to do it. Let's consider a slightly more complicated knot. Let's consider the figure 8 knot. Now we want to turn the figure 8 knot somehow into a braid. So you might try and do something similar. You might be like, oh, let's pick some point, and you might want to cut it somewhere. But if you cut it somewhere, notice, oh, this is no longer a well-behaved braid. You no longer get that it's just one strand crossing under the other, right? You start having some weird things going on, right? Like try and draw this, and you would have these two strands, but then this one somehow like comes down and goes under it and doubles back up and comes over. It's like doubling back on itself, right? In some weird way. And it's like, that's no good. In our braids, we don't want to allow any kind of doubling back. So what does that correspond to in the knot? Well, if we look back in this example, this braid worked out really well because braids are just things that continuously move down. You braid in a downward way, you never come back up. And in this knot, moving down the braid corresponds to moving counterclockwise. And notice everything is oriented so it moves counterclockwise about some central point. So we're able to move this counterclockwise orientation into a downward braid. But in the figure 8 knot, if we give it some orientation, we try and make it go counterclockwise. We try to make it, oh, now suddenly some of it's going okay. This is going counterclockwise, but then you have this bit here that's going the wrong direction. So when you try and turn it into a braid, it tries to go back up the braid somehow. And that's problematic. So you might think, well, maybe this one we can't turn into a braid. So somehow we need to move into a braid. We need the knot to always be counterclockwise with respect to some point. with respect to some center. So let's look at the problematic area. The bad part is this section right here. Right, this is where it's moving the wrong direction. The rest of the knot, you know, it's good. It's moving counterclockwise. Here it's moving clockwise. Here's where the trend was reversed. And so what we're going to do is we're going to take that little part of the knot, the bad part, and we're going to say, well, how can we fix it to make it so it's moving the right direction? What might we do? We want it to be moving the opposite direction, so how might we do that? It's moving this way. We want it to be moving this way. Yeah. Yeah, we're going to grab it and pull it over our center point. And so what we're going to get is we're grabbing him, we're pulling him over, and so you'd end up with something like this, where now this is an overcrossing, because I grabbed this yellow part and I put it over. And now this is all gone. And we have something like this. So now we check, is it all moving in the right direction? Yeah, now it's all moving counterclockwise like we desired. Okay, this is a little bit awkward here. You know, if you want to, you can smooth this out a little bit more. This is just coming under and connecting, so you can smooth it out a little bit more if you want. But notice now it's all moving the right direction.
Does it matter that it's not connecting to anything up there?
It is connecting. It comes around, over, under right here. Yeah, I took that segment, but it's still connected right there. Yeah. So all I did is I took the segments. So what I did is I took the overcrossing. You could also do it with the undercrossing. That is clockwise, and I pulled it over to make it counterclockwise. And so let's check that we have a braid now. So how many strings would this braid consist of?
3.
Yeah, so you start out with some strand, and here you have 3 strings. And let's track the story. Let's say this is like string 1, string 2, and then the furthest inside is string 3. So the outside string, whatever one's most on the outside is this one right here, is string 1. Okay, so 1, 2, 3. So what happens first? What's the first thing that happens as we move around this guy?
2 under last 3.
Yeah, 2 under 3, that's exactly right. So 2 goes under 3. Okay, what happens next?
1 goes over 3.
Yeah, so we just did 2 under 3. And next we have the outermost one, so 1 goes over the one that was next inside, so 1 goes over 2. So 1 will go over 2. And so now where are we in the story? So now we've accomplished this. We keep moving around. We have this incident, so what's going on there?
2 goes under 3.
Yeah, 2 is going under 3, that's exactly right. 2 is going to go under 3. And so now we've accomplished that. And so the last move is?
1 over 2.
Yeah, 1 over 2, great. 1 goes over the 2. And then you reach back to here. So now we've managed to turn the figure 8 knot into a braid. And if you were to close the braid up, take this bottom, glue it to the top, or stretch the string around, you'd recover the figure 8 knot. And hopefully the algorithm is general enough you can convince yourself you can always do this. You take some diagram for a knot, you try and put a dot in the center, you orient it. If it's not all going counterclockwise, then you take the bad pieces, you pull them over, pull them under, until you get it all in the right direction. And so you have some opportunities in your problem set to try that out for yourself. Okay, so now we have this thing of braids that represent knots. We can think of a knot by a braid. And so we need some way to talk about braids, because it's like, you know, if you wanted to describe this to your friend, like over the phone, it would be kind of tough to do, right? So we need some language to describe braids. So I'm gonna come up with some way to describe braids. So these are called braid words. When I have a braid, and it's just the first strand crosses over the second strand. So maybe there are more strands, however many more. Say it's 3 strands or something, but the first one crosses over the second one. I'm going to call that sigma 1. And if I have the second strand crosses over the third one, so the second strand crosses over the third strand, I'll call that sigma 2. And in general, if I have lots of strands, but I come up to the kth strand and it crosses over the k plus 1 strand, and maybe there are more strands after that, but when k crosses over k plus 1, I'm going to call that sigma k. But more can happen in addition to crossing over. You might also cross under. You might have the first strand crosses under the second strand. So what should we call that? Well, it's like sigma 1, but it's doing the opposite, so I'll call it sigma 1 inverse. And you might have the second strand crossing under the third strand. So it's like sigma 2, but it's going under instead of over, so I'll call it sigma 2 inverse. And similarly, for sigma k, you might have some k strands, but then the kth one comes under the kth plus first strand. Maybe there are more strands after that, but I'll just call this sigma k plus sigma k inverse. And now that we have an alphabet, so this is going to be our alphabet. We can make words to describe braids. And so what you do is you look at a braid, you begin at the top, and you start calling off what happens. So the first thing that happens here is a what?
Sigma 2.
Yeah, the second strand crossed under the third strand, so it's sigma 2 inverse. And then you go down, the next action to happen was, the first strand crossed over the second one, so it's sigma 1. And the next action is, the second strand crossed under the third strand, so it's when there's 2 strands interact, you name it based on the smaller one, so it's going to be sigma 2, because sigma 2 is interacting with its next neighbor. Sigma 2 is going under, so it's sigma 2 inverse. Now there is no sigma 3 here, because a sigma 3 would be the third strand interacting with the fourth one, right? So there won't be any sigma 3s. And the last interaction right here is, it's just sigma 1, because the first strand is crossing over the second one. So sigma 1. And this is a word that describes a braid that closes up to give you the figure 8 knot. Make sense? Okay. Well, you look at these words and you think, well, these words are kind of, these are interesting names. So we have, when you combine the letters, it's just stacking these on top of each other. And so let's think about why I use this inverse notation. What is like sigma 1 inverse? How does that look? That word, sigma 1 inverse.
Just like one string line on top of another string.
Yeah, so you have sigma 1 comes, and first sigma 1 crosses over, so the first strand crosses over the second strand. But then sigma 1 inverse happens, so the first strand crosses under the second strand. Right. And it could be in some larger braid. There might be some other strands here.
So they cancel each other out.
That's right. Like this braid is not braided. That's just when you have, well, what is that? What kind of move is that in our language of knot theory? Yeah, that's a Reidemeister type 2 move. It's a poke, right? Like that is equivalent to if they were just laying next to each other. And maybe there's some other strand next to it still. And so this is equivalent to, well, we should have some name for when all the braids are straight. What should we call that? Maybe we'll call this 1. It's like identity, right? You can call it U or E. I'll just call it 1. It's not braided. And so sigma 1 inverse gives you 1.
I think you accidentally did that with one of your other braids, your trefoil braid.
You think something's wrong with the trefoil braid?
Yes, I believe so.
No?
Mm-hmm.
Yes. He's supposed to go under, and this guy was supposed to go under right here, wasn't he? Because it goes under. That's right. So this better be going under right here as well. Otherwise, that part would be trivial. Yeah, very good. Good catch. Okay, so that's the trefoil. The trefoil, what's the word for the trefoil? How would you describe this braid that closes up to the trefoil?
Sigma 1, sigma 1, sigma 1.
Yeah, it's just sigma 1, and then another sigma 1, and then another sigma 1. So I'll just call that sigma 1 cubed. And that's going to be the word that describes the braid that, in this case, closes up to give you a trefoil. Very good. It goes under, so it's sigma 1 inverse, so it's sigma 1 to the minus 3. Sigma 1 inverse, sigma 1 inverse, sigma 1 inverse. Yeah, good catch. Okay, so we have a sense that this alphabet, we're just multiplying, right? This is like multiplication. And so our word is just composed by a bunch of letters, and we can multiply braids by stacking them. So we'll say by stacking. So for instance, if I had some braid like, here's a simple one, and I want to combine it with another braid, I just stack them. So maybe I'll combine it with this braid. The top braid here has braid word sigma 1, the first strand's going over, then sigma 2 inverse. The second braid here has braid word sigma 1, and then sigma 1 again, so sigma 1 squared. And so when you combine them, what's going to be the resulting word of them combined? Well, it's just these guys stacked together, so it just gives you sigma 1, sigma 2 inverse, sigma 1 squared. So you just concatenate the words, you stick the one word at the end of the other in order to symbolize stacking the braids. So stacking the braids is multiplying the words together.
Doesn't that mean that you can have inverse braids that cancel each other?
Oh, very good. What would be the inverse braid of sigma 1, sigma 2 inverse?
Sigma 2, sigma 1 inverse.
Yeah, let's test that out. So if we draw this guy again, and if you want to undo this, you claim that the inverse of sigma 1, sigma 2 inverse should be what?
Sigma 2, sigma 1 inverse.
Sigma 2, sigma 1 inverse. And the reason it makes sense it's probably the inverse is because algebraically, when you combine these, you would get sigma 1, sigma 2 inverse from the first one, then sigma 2, sigma 1 inverse. And so then that becomes, well, the sigma 2 inverse, sigma 2, these cancel, giving you just like an identity element. And then you have just sigma 1, so this is equal to just sigma 1 times sigma 1 inverse. But then those cancel, leaving you just identity. And let's see that happen. Let's draw sigma 2 first. So here 2 is going to cross over 1. And then you're going to have 1 inverse, so 1 is going to cross under 2. And does that give you the identity? Yeah, because you can pull the strand over, and that'll straighten out that part, and then you'll be left to something that looks like this. Exactly what we did here. And then you can pull him over, giving you just the identity braid. So multiplying our letters in the word corresponds to multiplying our braids. So if we look at observations, so far we have, what do we know about multiplying? We have, so in this set, we can stack, so we can combine, and there's some identity. So we have an identity. We have inverses. And of course, stack anything with this, it stays the same, right? You put this under anything, it doesn't change the braiding. You have inverses. In general, what's the inverse of, let's call it sigma I1 to the K1, sigma I2 to the K2 through sigma IN to the Kn. What would be the inverse of that? Yeah, what we did here is when we had to go in opposite order, right? We had to undo the bottom first. And so we have to first get rid of this last term. So his inverse needs to be a sigma IN to the minus Kn. And then you go in backwards order until you get to the first one, sigma I1 to the minus K1. Because if you stick these words together, then they cancel off in pairs, like chopsticks, right? Okay, so we have an identity, we have inverses. You can also check like other nice properties hold. Like if the thing about this is multiplication, well, is it commutative?
No.
Why is it not commutative?
Because it has to be paired with their inverse.
Yeah, like a simple example would suffice, right? If you have sigma 1, sigma 2, that's going to look in a 3-strand braid. You do sigma 1 first, and then you do sigma 2. And then you might ask, well, is that the same thing as sigma 2, sigma 1? So let's think. Sigma 2 first, so he's going to go over. And then you do sigma 1. So sigma 1's going to come over. Are these the same braid? Yeah, just by looking at it, it doesn't seem like they are, right? So it doesn't seem like it's commutative in general.
It's a mirror image.
Very good. Yeah, it's a mirror, and we've seen that the closure of a, so this will close up to a knot, and knots are not always equivalent to the mirrors. The trefoil, a right-handed trefoil is not equivalent to a left-handed trefoil, and so these wouldn't be equivalent either. They're like mirrors of each other. Okay, but it's not commutative, but it is associative. So what is associative? It just has to do with the order in which you stack them, and it doesn't matter if you combine these two and then add a third one, or you combine the last two and then add the first one. So it's pretty easy to see it as associative. So if you look at the set of braids, these are braids with some fixed number of strands. You know, you can't combine 2 strands or 3 strands. So braids with like n strings. If you look at like braids with n strings, you have some group with an operation that has an identity, that has inverses, and that's associative. Wait, I just used a word, didn't I? What is this? Those who have taken abstract algebra.
It's a group.
This is a group. So this is what we call a group. So this is we have a group. This is the braid group with n strands. There's one for each end. So a group is just some nice set that has these 3 properties. And abstract algebra, group theory, looks at and studies the properties of groups. And so what we have now is this really nice group structure. Now, when we were studying knots, think back, when we were studying knots, did knots form a group? We have a way to combine knots.
Yeah.
What's our way of combining 2 knots? Connect some. You take a knot, you take the unknot, you break them open, you combine them, right? And is there an identity element? The unknot, you connect some, anything with the unknot stays the same. Do you want to see a demonstration of this? Right, you take a knot. So here's some knot. I'll make a trefoil really fast. I'm going to break it open in a second, but a trefoil. And then you take the unknot, and I'm going to combine them by very carefully breaking open the trefoil, but keeping the knot in this. I'm not going to let it loose. Breaking open the unknot, putting them together. And what do I get? Just a bigger trefoil, right? So you can, so the unknot becomes an identity element. So we have an identity. Associativity is probably fine. You have a knot, you combine it with another knot, and then combine that with a third knot. It's probably the same as combine the last two and then combine the first one. That's not a problem. But do we have inverses? What would that need? You would need a knot and connect summit with another knot to get out the what? The unknot. Why can't we do that? Why?
Because of the determinant.
Last lecture,
Yeah.
The determinant stays like, you can only go up from the determinant. Like the determinant.
determines one way, but last lecture we saw
You can't add
the genus. The genus is additive. So if you have one knot and it has some genus like genus 2, any knot you combine it to with, it gets a bigger genus. And so you can never get down to a genus 0 unknot, right? So you don't have inverses. And so this is one reason why you might think braids are an interesting thing. They're like knots, they're related to knots, but they have this additional group structure with them. And so that's a really nice promising thing. Okay. So the question I want to ask now is, how do we know if two braids are the same? It's very similar to the question we've asked about knots. How do we know if two braids are the same? Or in particular, if two words, some sigma 1, sigma 2, etc., represent the same braid. So let's try and formalize some moves that we can do on braids to keep them the same, and think about how that impacts the words. So what's one move we've already seen that we can do with braids? Yeah, there's this. If you have some braid like this, you have some poke, then you can just straighten it out, and it's going to stay the same, right? So what is that doing to the word? You know, there could be other stuff going on in this braid also. There could be, you know, up here some other things going on. It could go under some other strand up here. You know, there could be all kinds of other things going on. But we're just zooming in to this one portion of the braid. We're just zooming into one portion.
It's just adding inverse to it creates an inverse pair. So
Yeah, so you're looking in the word of the braid, and what you're going to do is you're going to remove, or if you're going this way, you're adding, you're going to add or remove some like, you know, like sigma 2 inverse, or sigma 3 inverse. So I'll just put sigma I inverse. Whenever you see that, you can delete it, or you can add it in wherever you want. Or you could also do sigma I inverse sigma I, you know, either way. So you're allowed to do this, and that's going to keep the braid the same. What else can you do to keep the braid the same? So this is like a Reidemeister type 2 move. Yeah. What else? Do we have a Reidemeister type 3 move? So Reidemeister type 3 it's a slide, right? So a slide is like you have something up here, and under it you have some crossing. And then what you do is you slide the top part over. And you say, well, let's instead write that like this. So I'm going to keep this crossing the same. But I just slid this guy from being over him. I just slid it on down, right? The braid's the same. So what am I doing to the words here?
you're pulling the word in form.
So let's just write this word down. So here I have, I did a sigma 1, and then sigma 1, and then right here is like a sigma 2. And then right here I have a, the first strand over the second, sigma 1. And he changed into, now the first guy I have is a sigma 2. And then here I have a sigma 1. And then it moves into a sigma 2. So I've slid a sigma 1, sigma 2, sigma 1 into a sigma 2, sigma 1, sigma 2. In general, you can switch sigma I plus 1, sigma I with, well, when you do this overslide, it just switches the I and I plus 1 to sigma I plus 1, sigma I plus 1.
Would that work with a minus if it were the other way around?
Yeah, you need to be careful. If you're mixing minuses and pluses, you're going to get in some trouble.
So-
But if they're all inverses,
No,
then you
not
can,
inverse. Like, could you do a sigma I? Could you make it a sigma I minus 1, sigma I, sigma I minus
yeah. So if it was I minus 1, you would just rename I minus 1k.
Okay.
And then, I minus 1 would be k, and then I would become k plus 1. And so, I and I plus 1 is the same thing as I minus 1, I minus 1.
Okay.
Yeah, you just need two guys like 1 and 2 that are next to each other. So this is how they behave if they're next to each other. What if they're not even close to each other? What if you have like, these guys are crossing, and then, in totally different strands, further down, you have these guys cross. So what's going on here? Here we have like this is like a sigma 1, and this is a sigma 3. What is that the same as?
Go like that.
Yeah, there's no reason you can't just slide this guy down. And so this is equivalent to,
No.
right? So now what you just go, I just move this down. So this is still a sigma 3.
That is a sigma 3.
Yeah, and this is still a sigma 1. Right? They just switched. And so we can switch sigma I, sigma j with sigma j, sigma I. Not always! Remember, we looked back here. Sigma 1, sigma 2, it didn't switch with sigma 2, sigma 1 because they interacted in a bad way. So when can we do it?
When they're greater than 1 part.
Yeah, when I and j are not too close. So when the distance between I and j is bigger than 1. So the absolute value between I and j needs to be bigger than 1. That's a good way of saying it. Well, we can see that if words, so I'll put it this way, I'll say braids are equivalent if they are represented by words that are equivalent up to a sequence of such moves. Right, that's what we've shown just now, that you can do any of these moves to a word, and it represents the same braid. However, if I want to call this a theorem, I need to make it a little bit more significant by adding an extra if. Braids are equivalent if and only if they are represented by words that are equivalent up to a sequence of such moves. That is that these are the three moves for braids. And if they're going to represent the same braid, then you can move from a word for the one representation to a word for the other representation via just these three moves. And this is a result due to Alexander. Before he did his polynomial stuff, he thought about braids. In 1923, he proved this. So, if you want to know if two braids represent the same word, if you want to know if two words represent the same braid, you just need to see is there some way to move through a combination of these moves. So I mean, we could do a quick example if you want. So you know, here's a little example. I kind of want to keep this up. That's okay. Let me go up here. So example. Here I have like sigma 2 inverse. I'll just use this one. Sigma 2 inverse, sigma 1, sigma 2 inverse, sigma 1. What kind of fancy stuff might I do to this? Just suggest a move, any of these moves. What do you want to do? Well, I can't do this one because the I and J are not, you know, more than one apart. You just have 1 and 2. So you have to do one of these. So what might you do? Yeah, I want to do a switch. Am I in a position to do a switch? No, because I have a sigma. I have inverses, so that might mess me up a little bit.
What you can do is add in some identity.
Yeah, so maybe this isn't very interesting, is it? Right, like you can add in some identity. That's kind of not interesting. So let's change the example a little bit. Let's make this. Well, I'll keep this here. I'll make this a 3. Let's make this a 3. Let's make this 1. Let's make this an inverse. And let's put a sigma 2 here. Okay, now what could you do? What would that be equivalent to? Well, you can switch these guys, the 1 and the 3. Right? So there's no reason not to do that. You get sigma 2 inverse, sigma 1, sigma 3 inverse, switched with the sigma 1, so it's sigma 1 inverse, sigma 3 inverse, sigma 2. And then what can you do? Yeah, you can cancel these guys out. And so then you're left with just sigma 2 inverse, sigma 3 inverse, sigma 2. Yeah, so these represent, so these represent equivalent braids. Okay, but let's get back to knots. So we know when words represent equivalent braids, but then it's natural to ask, well, is it possible for two different braids to close up to the same knot? So, question. Can different braids close to the same knot or possibly a link? Could you think of a way that's possible? Two braids that are different from each other, but somehow they close up to the same knot or the same link.
Maybe you have one with 2 strands and another one with 3 strands, but because of the way you were wrapping it, they're actually the same.
Good. So you have somehow like a dumb extra strand.
Yeah.
So let's try and think of how we could do that. Let's go back to the trefoil example from before. So we have, here's the 1, 2, 1, 2. So here's one braid that closes up to give you the trefoil. So he's going to close up to give me a trefoil. Now what you want to do somehow is add in a 3rd strand. So let me draw another copy of this. So here's my trefoil, and we're trying to add in a 3rd strand. Now, if we simply kept him there on the end by himself, we wouldn't get the same knot. We would have this knot plus just some second component, right? So you can't just add a third strand. So what do we need to do in order to make sure we still have one knot?
You can slide the two endpoints over and slide along the last.
Yeah, we need to make sure this last strand interacts with the other one, right? Like switches places with it. So let's change this a little bit. Let's take this last strand and say, well, we want to get him to interact with the other ones. So let's add one more move. I'm just going to move this last strand so he's no longer in the last position, but he's in the second position. Now what happens when I close him up? When I close him up, notice it's just one component now. You can trace around the whole thing. Say with red, I'm in the third position. I start off in the third position, but then I move to the second, the first, the second. So I traced out the whole thing. Are these two knots equivalent? How do you know they're equivalent? How can you see that they're equivalent?
So if you take that extra strand on the outside and you just twist it, then it's going where the red and white.
Yeah. Yeah, that's good. So I'm going to take this third strand, like, how do we see it?
Well,
This
you can
third
wrap
strand,
it the other way.
Wrap it around.
this third strand right here goes like this, right? And you can imagine pulling it behind, and if you just pulled it all behind, you just twist it like you said, you would end up with this guy, instead of coming down here, you would connect right there, right? You pull back that red strand, that you can erase that red strand we drew and pull it behind, and then you're left with just this. Because he's just doing an unnecessary task of going around before hitting here. You just had him go around a second time, but then arrive right back here. So we added a third strand by putting a little twist at the end, but it didn't change the knot. So if you think, if this guy has some word, if his braid word is W, so that'll be the braid word for this knot. What would the braid word for this knot be? Yeah, it's W. It's the same braid word as before. This word is exactly the same as it was before, but then you added something to the end. But you added some sigma 2 to the end. Right? So here, these two words represent the same knot. So this move right here is called stabilization. Because it's stabilizing a knot by removing an unnecessary extra strand. So you can add in or remove a strand. So by putting a W2 at the end. Well, what can you do in addition to putting a W2 at the end? So let's draw this in general. In general, you have some braid that comes around some number of times. So all we've done here is we said, well, what you can do is you can come and add some new component, but then you need to get him to just interact like that. Maybe that's an easier way to see it. Because what you can do is just pull the red strand and it's back to what you had before. So what stabilization is doing is you're adding, if you have, let's say originally you had two strands. So if you start with n strands or n strings, you can add a sigma n or sigma n inverse to the end at the bottom, or you can put it at the beginning up top. You could do it inside and put it at the beginning. You could put a sigma 1 or sigma 1 inverse at the beginning. and that won't change the word that's represented. So this gives you the figure 8 knot, but this guy with a sigma 3 is stuck on the end would also give you a figure 8 knot. And I think we'll do an example of that in a second. Okay, there's one more move we can do to change the braid, but make sure it gives us the same knot. Can you think of what else you could do to change the braid, but keep the knot the same?
Flip upside down.
Oh, so you might get some kind of mirror image or something. Or like literally flip it upside down.
And the diagram.
Yeah, I don't know if that really does anything. What do you mean by like some kind of like mirroring?
Or like if you rotate the diagram 180 degrees.
Oh, okay. Yeah, okay, those are dumb. So up to symmetries, yeah, you can rotate it. Yeah, you know, you can change the angle you're looking at it. That's fine. I mean, we're assuming we have some orientation, so we're assuming there's some natural up and some natural down. Well, let's say we have some braid. So let me just draw this abstract picture. And maybe it's a braid of many strands. Let me make 4 strands. Now, we said we can come on here and like add a new strand, but what if I just want to tinker with these existing strands? Am I allowed to simply stick in like a sigma 2 into here at the beginning? Could I just put a sigma 2 at the beginning? Would that change the link? You better believe that would change it, right? Like if you have like the hop link, like if I have this link, like this is unlinked, right? But if someone comes in and they just like insert, now it's linked, right? I finally change. Oh, now it's a single component. Yes, it's an unknot. So one time 2 components to 1 component. So I totally changed the game. So I can't do that, right? I'm messing things up. But I could do that if I also then undo that. I could do this if I then also did, well, let's see. Oh, nope, I want it to look like, I can undo it, right? So now I'm undoing the move, except instead of undoing it on top, I'm going to move this undoing of it to the bottom. So I'm going to slide that around to the bottom. So on the bottom here, I have, is that how it should look? Yeah, because then I can just stick them inside. So what did I do to my braid word? Originally I had some word W. I had some W, but then what did I do to it? I stuck something at the beginning, whatever I want, you know, an S2, an S3, an SI to the beginning. I then have the same braid, and then what do I have afterwards? The inverse of it. Sigma I inverse. And this is called, and if you study group theory, you may have seen this before, this is called conjugation. So I've changed the word, but it represents the same knot or link. Well, we can play this game all day. You know, it's like we can stabilize, we can conjugate. What else might we do? Markov showed that's it. In particular, if he showed that 2 words represent the same knot or link, that is, they close up to that knot or link, if and only if they are related by stabilization conjugation. Or these other moves we talked about earlier, right? These moves that Alexander said, the moves that don't even change the braid. Because if you're not changing the braid, then of course you won't change the knot either. Or the 3 moves that preserve the braid. So let's just list our moves. So I'll call these knot / link preserving moves. We'll just summarize by listing all 5 of them. There's the original 3. What was the first thing you could do? You can add or remove. You can add / remove your sigma I inverse, or the inverse of that, sigma I inverse sigma I. What was the second one?
You can do the switch.
Yeah, you can switch sigma I sigma j with sigma j sigma I, as long as I and j are not next to each other, as long as the distance between I and j is bigger than 1. You can, what's the, the funny Radamaster 3 type move. You can also switch, if you have sigma I plus 1, sigma I, that can be switched with sigma I plus 1, sigma I plus 1. And then we have the 2 moves that correspond to stabilization. So you can add, so let's say this is a n string braid that we're talking about. So you can add a sigma n to the end, or sigma n inverse. If you can add, yeah, so either one to the end, so sigma n or sigma n inverse to the end, or sigma 1 inverse to the beginning. Probably only 1 n in beginning, isn't there?
No.
Well, this.
You had it right.
Oh, there's actually 3 n's because of the.
Just add enough that you know you got it.
That's right. I got those ends covered. Or you can conjugate. You can move w into some kind of sigma I w sigma I inverse, back and forth. So let's do an example and convince ourselves that this is true. So I want us to come back to our figure 8 knot. I want us to take this word we have for it, this guy, and I want us to mess the word up using these moves, get a new word, and then see what that braid is. So we have this word. So what's one move you might do to this word? Give me something.
Add a strand.
What do you want to add?
A sigma 3.
So yeah, if we want to add a strand to it, we need to add a sigma 3. So this is equivalent to sigma 2 inverse, sigma 1, sigma 2 inverse, sigma 1. And then we added a sigma 3. What else might you do to it?
Twist it at the beginning and then twist it at the end.
Okay, so you want to put something on either side. So I'm going to put like a sigma 1 inverse on one end and a sigma 1 at the opposite end. Okay, so I can do that and I keep the word the same. So it's sigma 2 inverse, sigma 1, sigma 2 inverse, sigma 1, sigma 3. Oh, what can we do now?
Switch 3 and 1.
Ooh, yeah. The sigma 3, sigma 1, sigma 3 at the end.
Yeah, so you can switch a sigma 3 and a sigma 1, that's fine. So that gives us sigma 1 inverse, sigma 2 inverse, sigma 1, sigma 2 inverse, sigma 1 squared, sigma 3. Because the gap between 1 and 3 is bigger than 1. My sigmas begin to look like deltas. What's going on there? It's a sigma. And you can continue to play this way. And if you want to, then you could draw the braid that corresponds to this. I don't really want to. You can draw this braid. You can close it up, and you have some diagram that you know is equivalent to the figure 8 knot. So it gives you a new way to get a totally different diagram for the figure 8 knot. And you could imagine you could make complicated unknots this way. You could begin with 1 for the unknot, so this is the figure 8. But if you wanted to make a complicated unknot, you could then start playing around with this and be like, well, that's the same as sigma 1, sigma 1 inverse. And that's why we can stick a sigma 2 at the end, you know? And you can keep going according to these rules, and you can make some complicated unknot if you wanted to. Okay. Well, there's one last question this raises that I want us to do in the last final couple minutes, and that's, we can notice now that you can draw the figure 8 with 3 strings, but because we can do a move like this, you can also draw it with 4 strings, right? So knots can be, so you have braids, different braids for knots with different numbers of strings. So you may wonder, what is the minimal number of strings needed in a braid to represent some knot K, or a link, it could be a link L, but some knot K. So it's an interesting question. We call this something. We're going to call this the braid index. This is the braid the braid index of K. And so, for instance, for the figure 8 knot, what is the braid index?
3.
Well, you can do it with 3, but how do we know if we could do it with, it might be 2, right? All we know for certain is that for the figure 8 knot, the braid index for the figure 8 is at most 3, because we found some braid of 3 strings. And you can try and convince yourself, you should think about this. What you can get the trefoil with just 2. What else can you give just 2 strings? Can you get the figure 8 just 2 strings?
No.
Right? You don't think so?
No.
Why not?
Because with the trefoil, with the 2 strings, all you can get are just sequences of just.
Yeah, you can just keep adding more twist, right?
Yeah, that's all you can really do.
And you can't get the figure 8 that way?
No, because if you add, because you put in the other twist, then it just undoes itself. So you can either add a twist or untwist. There's no.
But 3 twists gives you the trefoil. Does 4 twists give you the figure 8?
No, it just gives you 2 links.
4 twist.
Yeah.
How about 5 twist?
Then it's like the star trefoil.
Gives you 5-1? Yeah, so you should think about this. So maybe you convince yourself. So maybe you think that it really is 3. But in general, this is a hard question. You're right. So it really is 3 for the figure 8. But in general, this seems like a really hard question. I'm holding in my hands a paper from 1987 by Yamada, where the title is called "The Minimal Number of Cipher Circles Equals the Braid Index."
Wouldn't the paper from 19-something be available?
No. So if you want to know what the braid index of the figure 8 knot is, so this is the theorem. Given the braid index of any number of knots, it's equal to the minimal number of cipher circles needed to draw a diagram for a diagram of K. So you look over all diagrams for K and you find the minimal number of cipher circles. Now maybe this is hard to calculate too, right? But at least we know it's equivalent. So for the figure 8 knot, can we draw the figure 8 knot? can we find a diagram that has just 3 cipher circles? Because if the braid index is 3, this should be a diagram with 3 cipher circles. So let's see if we can, I'm going to try and make sure I draw this correctly. So here's my figure 8 knot. Well, let's just do it the dumb way and see if we get lucky. So you give it some orientation. And then you go around and you smooth out all of your crossings. So like this gets smoothed out like this. And what happens here? This guy's coming down, so it gets smoothed out like this. And this gets smoothed out like this. And here he gets smoothed out like this. And like this. And he gets smoothed out here and here. And so do you see what you have there? Yeah, you have 3 circles. You have like a kidney circle, and you got a circle down here, and a circle up here. And then those circles are connected by, some crossings. They're connected by this crossing, they're connected by some crossing, and by some crossing. But you can do it with just 3 circles, so you know the braid index is at most 3. And then you can try and convince yourself that you can't draw the figure 8 knot with just 2 cipher circles. You always need 3.